Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about low temperature thermal desalination. So let's dive deep into it. Now, why do we need desalination? Well, factual reality is that world is running out of fresh drinkable water or potable water. We are running out of it. And why is that? Well, rain is unable to replenish our consumption basically. So we are consuming 10,000, rain is barely adding 5,000 to it. So basically it's running on a deficit, so to say. So it's running there. And most of the rainfall, you may think like, okay, I built a dam, it exposed way too much of a river to air, as in like winds and sunlight. Now that will cause a boiling issue. Okay, but it will fall down on rain. Yes, there's a problem with that. If like every time water goes up, it's rolling a dice where it's gonna fall. Yeah, 70% of the time it's gonna fall on the ocean, surface area wise. So that creates an issue, and as the land gets hotter and hotter, yeah, that probability tilts just a little bit on the seaside. So you can understand the issue. And not to mention, because of our mess up with the whole bio ecosystem, we changed it way too much, so it's way too chaotic. So even though we have hundreds of dams, we still have flash floodings, because again, the dams are designed for one sort of water flow architecture, which we have changed, so it's no longer effective. And flash flooding, even though it's a news in every country nowadays, it's not actually recharging the water, it's just contaminating. And worst case scenario, it's contaminating almost isolated places of water, which is really, really bad. So flash flooding does not recharge the H2O as quickly as we want it to. So things are bad, and let this be very clear, it's planet-wide. So this is China's drought map, bad. This is America's drought map, really bad. Europe's drought map, super bad. I'm not showing India's map because all Indians already know it. We get it in newspaper almost monthly. So things are bad. Now, thankfully, there is one good news, that Earth has more than enough water. Like, water is not an issue. H2O, we good, we got it. It's just that we need to remove the salt from it. So NaCl, basically, we have to remove that puppy. If we can remove that, problem solved. Okay, we must have technology to remove it, and we do. So what's the problem? Well, problem is it must be cheap and abundant. You have to understand, we consume a bonkersly large amount of water, idiotically large amount of water. So that's not something where you can do non-abundant sources. For example, many times, almost periodically every 3 to 5 years, somebody will smoke and they will be like, okay, what if we extract water from the air? It's like, that's called humidity. If you condensed all the humidity, there is not enough water to feed even a small city, let alone a metropolitan. Just not there. And what time that is enough moisture would be there? When it's raining. Do rainwater harvesting, far more cost effective. So not only you need something cheap, you also need abundant. So these two technologies, basically criteria, are very difficult to do. We know how to do desalination. We have known this from 1800s. So the question is it cheap and is it abundant? So these are the two vectors for it. And India is on the serious scenario, so to say. So let's understand some facts that will clarify why it's no so easy. Well, here's the deal. You must think about, hey, what if I take the water and boil it, like how Joe Rogan asked? And here's the deal. You can do that. But if you do it on a vacuum, basically you take a water and you just like, okay, boil it. How much energy it would take? It will take 620 kilowatt hour or 620 units to get 1 ton of water from evaporation entropy calculation. Like, that's bare minimum. Now you can understand that 620 units of electricity is a lot, and having that much just for just 1 ton of water, and if you're like, hey, I have no context for 1 ton, thankfully water is awesome in that regard, or we humans made our measurement system on that. Yeah, 1 ton simply means 1 meter cube, and like, okay, I do not understand that, that's 1000 liter. Everything is perfect on water. Again, it's not absolutely perfect, but you get the point. It's more than good enough for normal day-to-day conversation. So that's a lot. Now, like, can we reduce that 620? That's the issue, right? We have the water, we have energy penalty. Can we reduce that? Yes, absolutely. We have done that from late 80s, I would say. Multi-stage flash evaporation. Basically, these puppies, the sole reason why you have water in Dubai and places like that. Basically, if you have a lot of energy, you can convert basically water into steam and recycle that steam condensation. Basically, you do not want steam, you want condensed liquid water. So when you condense something, it has to dump energy. What if that dumping energy goes into the next stream? Basically, you preheat water. So you can do this almost 4 times. Now we have managed 4 or 5 times, and voila, these are the reasons. And what kind of energy efficiency we are talking about? We are reaching real world 70 to 100 units of energy for basically 1 cubic meter of water, 1 ton of water, so to say. So that's very good. Like we started from 620 and we are like, we're good. But here's the deal. If you compare water consumption, yeah, this is untenable. That's why even though this technology was there from like, 70s, only OPEC nations can afford to do this. This is too expensive. It's too idiotically expensive energy-wise. Remove the penalty, environmental degradation, remove all of that. Just the energy cost, you will go bankrupt if you try to run a country on this, unless you are lucky enough like OPEC. So that's an issue. And that's why Israel did not invest too much money into this, nor America did. However, that was brute forcing it, like you're boiling it. What if you tricked it? Basically, how nature tricks it using osmosis. So what if you reverse that process? Reverse osmosis. Now, reverse osmosis is the best system as of now because it bypasses this need. You're not doing phase change. Phase change consumes bonkers amount of energy. So what if you do not do phase change? So that's the core reason why reverse osmosis is energy efficient. Now, what kind of efficiency we are talking about? Now, when this started to come into the market, game changed. It started to drop the energy consumption. In the latest and greatest system that Israel has, it has almost touched 2.8 units of electricity per cubic meter of water. That's efficient. And like even the sloppy plants, some plants in California, they are also reaching 4 kilowatt. So compared to 100 kilowatt hour, 100 units, you are dropping it to 4. It's bonkersly energy efficient. It just comes with two penalty. Penalty number one, the technology. This technology is expensive. Like that's why Israel can do it. Not every Tom, Dick and Harry country in Africa can do that. Is beyond belief expensive. Like the membrane technology, yeah. And not to mention the membrane wear out. It's not something like, oh, once I put it, it's gonna be there forever. No. Again, depending on the design, depending on the criteria, they will tell you like you have to replace it 5 years, 10 years. You have to do it. So it's expensive AF. And early days, it was not even this efficient. The only reason why this is this efficient now is we figured out that once you put water into it, like that pressure into it, yeah, reverse osmosis, you are forcing something against the grain, so to say. So it requires a lot of oomph. How much oomph? Let's say 50 bars of water pressure. That's a lot of oomph. Now, here's the deal. The old system was membrane, good water, bad water, done. So somebody figured out, hey, what is the pressure of the bad water? It was 40. So you put 50, only 10 was lost. So you had 40 bars. So somebody figured out a new technology known as energy recovery system. So the basically pressure recovery. So that input water, or pardon me, the reject brine water still has pressure, still has 40 bars. You try to dump that 40 bar into the incoming water stream, and now the energy consumption goes down. So again, it does not transfer 1-to-1. So if you dumped 50, it got 40 out, that 40 may transfer 30 bars into your incoming stream. But again, normal stream going 30 plus, that means the delta is only 20 bars. That's still good. So that's why we do pressure recovery. And that's why we can achieve 2.8 units of electricity per cubic meter. This is becoming almost good. Almost. It's like, almost good. Meaning, if you're in a water stress scenario, this is like, we can do it. It's like uncomfortably expensive, but like, I can do that. This is not. This is like, unless you are blessed by oil gods, you're not going to do this. This, you can do it, but it just comes with two penalties. Bonkersly high capital cost and ludicrously brutal brine water. So that's the another aspect of it. What happens to the waste? Well, generally it's a brine. Okay, so it's a very salty water. Basically, you remove the good water, it only has salt. So let's quantify that in X. So the technology that I'm going to talk about today, it barely goes to 1.1x, meaning it's 10% increase, barely. Now, multi-stage flashing, it can touch 1.5x, meaning the salinity goes up by 2. And then you have reverse osmosis. Yeah, that's a 2x system, meaning the water that when the first plants were built and we dumped that water, it sterilized that area. No fish, nothing. It's just like whoosh, Dead Sea. So it's a very bad system. So we have figured out very early on, because it was that concentrate, so to say, that brine cannot be directly dumped. So we had to have extra pumps and collect a lot of fresh water, as in this scenario, seawater that is untainted, and slowly dilute it. So ratios had to be figured out based on the area, temperature and all that. So yeah, it's a very destructive to the biosphere. Energy wise, super awesome, but biosphere wise, yeah, it's a nuke level option. This is a minor war, this is a nuke. So that's why LTTD is so awesome. It's like almost negligible. From biological point of view, it's like, oh, it's a bit warmer, so salts are a bit higher now. It's not dangerous or like life ending. And we must manage it cost effectively, otherwise it's gonna fail. There were many plants built during the drought era, and most of them shut down because, again, once or two random rain happen, and then people are like, it's not that cost effective. Again, that's why, like, every time you say, oh, why don't we reverse osmosis it? It's expensive. It's expensive AF. Google the price of that pressure recovery system. And be mindful, you only have two options. Either you invest boatload of money, or invest boatload of money with a truckload of money, so you can actually run it for long enough. You will, that 2 to basically 2.8 to 4 kilowatt hour, the gap is huge. And again, you will be making million cubic meters or million tons per day, so to say, for running a city. So it piles up very quickly. So these are the absolute real world fact with real reality. So what is this LTTD? LTTD is basically tricking the water rather than boiling the water or forcing it through a membrane. It's like, what if we boil it but without temperature? It's like, how would you do that? Thankfully, Earth has a pressure. Pressure is 1 bar or 15 psi. What if you have normal water, as in 24 degrees Celsius normal water, average water, room temperature water? You take that 24 degrees Celsius water, put it in a chamber and pull a vacuum on it. How kind of vacuum? Again, generally you're supposed to measure in millibars. It sounds weird to me. So, okay, 0.3 psi. So what happens then? It boils. Okay. So how low we can go? Like how low of a delta? Because yes, everything depends on temperature delta. If your hot water is hot or cold water is cold, it will work. But what is the gap? At the end of the day, it's always about the gap. So same as in jet engine, what is the core flame temperature versus what's the outdoor temperature? The greater delta, better it would be. Same goes in combustion engine. We want the cylinder to and the outside to be cold. The cold and hot reservoir, that's it. So it's not about pressure or temperature, is about the delta. So this technology allows your delta to be 8 degrees Celsius. So if you have a cold reservoir that is very cold or hot reservoir that is hot enough, how hot? 8 degree, as in like you can have normal solar concentrator, it will give you that kind of temperature delta. It will work. That's the good part of it. And why would it work in terms of phase change? Again, you are pulling it at 0.3 psi, almost pure vacuum. So that's how it works. Now, where would you get that sort of temperature delta? And again, the moment you start to talk about, oh, I'm going to heat water to 8 degrees Celsius. Yeah, I do not know if you know this. Water heater costs a lot of energy. And you're talking about thousands of liters, millions of liters, billions of liters. Yeah, even increasing 1 degree Celsius, it's a bonkers amount of energy. So Indian scientists came out with the idea, hey, we have thermocline, meaning if you take seawater, different depths have different temperature. So surface level, 24 degrees Celsius, although to be fair, for India, it would be 10 degrees Celsius hotter. Tropical regions are a bit hotter. So 24 degrees, meaning if you have a pipe that is collecting water from, let's say, 10 meter deep or 20 meter deep, you're going to get 24 degrees Celsius water. Cool, awesome. But what if you have a pipe that goes deep? How deep? Let's say 500 meter. Yeah, your temperature directly dropped to almost 12 degrees Celsius. Yeah. And what about summer? Here's the deal. Summer, both will go up. Winter, both will go down. And the gap, the delta will always be above 8. But what if you're rich? You can increase the depth to 1. Now you're reaching 8 degrees Celsius. What if you want even more? 1500. Generally, it's said like if you go way too deeper than that, pumping loss will increase so much that it's not effective. But generally, this is the sweet spot. 500 meter to 1 kilometer. If you can get this zone, you have enough delta to do all the boiling action from sea itself. Let that be very clear. All the boiling energy is coming from the sea. The hot reservoir and the cold reservoir is the sea itself. You are not creating it. That's why it's so energy efficient. So what do you spend energy on? Pumps. Vacuum pumps and water pumps. That's the only thing where you are dumping energy into. And brine is negligible almost, because again, inherently you are boiling things at such a low delta. Compare that to 30 degrees Celsius delta or 40 degrees Celsius delta of other systems. It's bonker. You try to boil as much water as possible. Consequence, the concentrate is very concentrated. It has very high brine salinity. This is negligible. It's like everything is calm. So how do we do it? Well, you take warm water, simply meaning surface water. Surface water goes into a flash boiler or basically flash chamber. This chamber, you pull a vacuum. Now, you have to understand that vacuum pump has to work 24/7 as long as the system is working. It's like, why? In most other system, you can pull a vacuum and then it start working. But here, because you are injecting normal seawater, it has to dissolve. It's basically eliminate its nitrogen content and oxygen content. There is a lot of that. And you cannot maintain vacuum here if you just do not remove them. You are removing water vapor, that's cool. But every time you're removing water vapor, you are trapping other gases there. So you must remove what we call non-soluble gases. So that gases has to be removed. That's why you have vacuum pump. So you take water, you pressurize it, you spray it in a chamber that is almost pure vacuum. Majority of it turns into steam, not majority, like you get the point, like enough of it turns to steam, you filter it through demister, and then it goes to a shell and tube condenser. In this condenser, you run the cold water as in depth water. The cold water condenses it. That's the hot and cold reservoir. Warm water and cold reservoir. This gap, surface and depth. That's all there is to it. And then you collect the fresh water out of it. And you have to keep running the vacuum pump so you can keep removing the oxygen and nitrogen dissolved. And there are certain systems that people are trying into that warm water intake, so it dumps de-aerate the water, so to say. So it dumps majority of gases before it goes into the chamber, because again, you do not want to spend too much energy on the vacuum pump itself. So inherently you only have 3 pumps: your cold pump, your warm pump, and your vacuum pump. That's it. Everything else is auxiliary. Inherently simple, just metal structure, and it works. So low temperature delta. Basically, you are utilizing vacuum to get this work, and utilizing the temperature delta of the sea surface. And again, you must have seen ocean thermal energy recovery system. That was the same point. So instead of trying to get electricity out of it, which is not that valuable simply because you get very little out of it, here you get far more valuable thing: water, fresh water. So this is LTTD technology. So let's come to India. Now, as of now, when I'm making this video, India is the only country and first country at this point in time that is doing this. 2024. Now, be mindful, we are not just, okay, we have one lab test. No, we're good at this. Like how good we are at this. In Lakshadweep, if you go into Google Map, type Lakshadweep, you will find there are a lot of small islands. 3 of those islands are this. So basically this puppy. So we built it, like I think the oldest one is Kartavati, that is in 2005. Then we built another one in 2007. Basically we built this whole puppy on a floating barge, 2007. Then we built it on a coal power plant waste heat. Basically be mindful that 8 degree is the delta. So your cold side could be surface water and the hot side would be surface water gone through basically radiator, I would say, or heat exchanger of the coal power plant. So you can cool the water, cool the power plant water, heat up the intake water. Now you have the delta, it will work. So that was in 2009. Agatti, that got its plant in 2011, and then Microna, that got its plant in 2011. And these plants are big, as in 1 lakh liter, 100,000 liter per day. Energy consumption is negligible. That's the plant. Nothing fancy, it's just a chamber. You just have 2 pipes, basically intake and exhaust. Nothing more than that. It's very simple, surprisingly simple. That's all there. And another one, coal power plant assisted, that was in 2009. I have no idea why National Institute of Ocean Technology, which is the puppy responsible in India for making this technology reality, they have thought to put this on a boat. You're like, wouldn't that make it great for Navy? No, you need a pipe that goes very deep. That's why I did not get it. Like, that's the only reason I can figure out. But again, the losses you will suffer from building all that stuff, the cost of extra pump and little bit of extra running cost, not that beneficial. But again, from a technological demonstration, is shut up, take money. We can build something that works on a sea surface vehicle. Yeah, shut up, take money. And all of these, they are still working. This is so common for basically people of Lakshadweep. They do not care about it. Like, yeah, it's a thing. It has been working. That island nation, it's almost island nation. They do not have to worry about it. And as we improve with solar, wind, there is an upgraded plant that is in works right now. They're going to use buoys to create mechanical energy. And that mechanical energy will directly do the pumping. So you will not even need that. The idea is to have sea giving you everything. The energy needed for pumping, the temperature delta needed for the actual process, everything directly from the sea, you just get fresh water out of it. And the penalty, again, it's very little. We have the system, we have the data, and these things are scenic places. Trust me, there are a lot of observation done regularly. So yeah, it's not contaminated like as it would be if it was a RO water plant, which is dumping water directly. So, and you can see, like, we started with 100 cubic meter of water per day. Then we went to 1000 cubic meter water per day. Another plant was like 150 cubic meters, and the 35 cubic solar one. We are also trying solar because again, you do not need a lot of hot water. 35 cubic meter water per day. Another plant is 100, and underway right now there are some under construction that is 1000 cubic meter. 2 of them. That's another power plant based, and another one is that is like a really high end one, which again I have no idea why they are so hell bent on offshore, but that puppy is 10,000 cubic meter. Yeah, that's a lot. That unit is so large. Now you're talking about a dam's power water delivery, like, you know, a dam reservoir is measured in those sort of unit. Yeah, it's huge. So that's offshore plant known as DPR stage, and then you have 6 multiplied by 150 plants for Lakshadweep. Basically, Lakshadweep have a lot of island. 3 island already got it, and it is so successful. They're like, what if we added more? So we got it. It's here. It's real, it works, and there is this is one of the rare times where I can genuinely say somebody in National Institute of Ocean Technology loved to make the video needed for, like, you know, you have to build these things and show it to basically bureaucrats. It's like what you're doing, or ministers sometimes. There's so much love put into it. It's a very ancient video, like 7 years ago, and made in very low resolution. But holy damn, you can see, okay, how the heck you built the pylons? How did you build the pipe? How did you anchor the pipe in the bottom? How did you carry the system? Everything was calculated. Basically, you did not have money. Like this plant, they showed like how the heck you carried such a big flash chamber. No, you build the bridge first. And again, that bridge will be the final intact. How do you make sure the cost is not high? Use plastic tubes, not steel tubes, because again, steel tubes will corrode in sea. It will corrode very quickly. So all of those data is there. What they did, how they, everything, pump, like what is the pump flow, 150 kilograms per second. 2 of those puppies. And then you have vacuum pumps. Everything information is available. I was like, damn. Only wish like they had better computer to do the rendering. So again, 7 years ago we had HD. So that's like, but again, it's amazing. Like somebody came up with the idea, they built it and it worked. Then we built another, it worked. We built another, we have a whole unit of it right now. So this is awesome. Like this is one of the few technology where it's like India is not only the first, it's leading. So what can we expect in the future? Well, reality is it solves our freshwater H2O problem. Every other system, again, RO is a real technology. It works, but again, it has penalty, not only in terms of cost, it's also bio damage, marine damage. Now, having a system that has less damage, I will take that over not having water or having too much damage. That's are the two options. So I'll take minimal harm to marine life. I'll take that. And there is no complex technology. This is very critical aspect. I can go to, let's say, Egypt and say like, rather than going boom boom on some other's dam, what if you use the goddamn technology? You are in tropical place, you have sea border, you have everything needed. Heck, you do not even, you have so much surface area, you can just put giant solar farm. You do not even need to, like, you know, even the electrical cost, you can keep running the plant 24/7. And be like, okay, we're done. We are creating our own river, freshwater river. They can do that. Like they can actually do that. You're like, okay, these plants are small. Again, we built small because it's a small island where we built it. It's a small test project. Each of them worked. Let's be very clear. It's not like could be, would be. And the budget it's not even millions of dollars. It's very small amount. And cost is available. You can figure out the cost of it because again, memorandum of understanding, and given it's a public funded research, you can easily find all the payment details on it. So no complex technology, no patents. That's good. You do not want to deal with that. Trust me. Like I'm not joking. I'm literally in talks with venture capital who literally building a new membrane research lab in Indian Institute of Technology. So we can build this sort of RO system. And this is like, I got this, bro. Again, that membrane technology will be needed for other things, but for water, we got this. You do not want to rely on patents for complex things, like for something as basic as water. So this is there. And it's a perfect sink for our waste heat. Our cities, coastal cities, have bonkersly large amount of waste heat. Like go to Mumbai, go to Chennai, go to New York, like bonkersly large amount of waste heat is created. What can we do? Well, you can do district heating. Again, more and more people are realizing, heck, people in Dubai realize that that's far better to have district cooling rather than just everybody trying their best of like to have a cooling tower which drinks water. Okay, district cooling. Again, it improves a lot, but what if you improved even more? Well, dump water into it, salty water, get fresh water. So not only will save electricity, if you have district cooling working with this, you will save fresh water because again, cooling towers will not consume it, and you will save electricity because again, this is far more efficient, and you get fresh water. It's a triple dipping solution. You solve all the problems. And same can be done with power plants. Again, we do not expect that to be much used in the future because again, coal is getting expensive, but it can be done in the meanwhile. And in other future, I can easily see this being used with thermal energy recovery system. Again, that also has waste heat. So might as well use it for fresh water. We always want it. A data center, everybody's like, data center is consuming so much water. What if instead of consuming water, it's like, what if it gave you water? So there is a lot of potential here. This is like one of those, it just works kind of technology. It's tragic that we Indians are so good at making things. Documentation is something beyond us. So this is a really good technology which is not made out of what if this, what if that. No, it's just like you take it and go. Like you can actually book a visit to there, go and visit the plant if you want to do that. So it's there. And I've linked one person video who actually went there. It's very simplified. You will think, oh, they will have control. No, it's a simple thing. It just pumps, 3 pumps basically. So it's a very effective utilization of resources we have. So this was my presentation on low temperature thermal desalination. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.